Hello aspirants, welcome to Magic World of Physics. In this video, we're going to discuss about some questions from thermodynamics and statistics which is asked in various exams like GATE, BARC, CHESS, TIFA. Hope this video will be helpful for your coming BARC exam 2026. Without any further delay, let's get started. The first question is, a gas of n particles is enclosed in a volume V at a temperature T. The logarithm of the partition function ln z is equal to n ln of V minus Bn into kBt the whole raised to 3 by 2, where B is a constant with appropriate dimension. If P is the pressure of the gas, then the equation of state is given by dash and the internal energy of the gas is given by dash. Given that ln z is equal to n ln of V minus Bn into kBt raised to 3 by 2. The Helmholtz free energy F is equal to minus kBt ln z, and this is equal to minus kBt n ln of V minus Bn into kBt raised to 3 by 2. The pressure P is equal to minus dou F by dou V, and this is equal to n kBt into kBt the whole raised to 3 by 2 divided by V minus Bn into kBt the whole raised to 3 by 2. So P into V minus Bn is equal to n kBt. So the answer is option A. Here the internal energy U is equal to minus dou by dou beta of ln z. That is, this is equal to kBt square into dou by dou t of ln z, where beta is equal to 1 by kBt. So this is equal to kBt square into dou by dou t of n ln of V minus Bn into kt the whole raised to 3 by 2. So this is equal to n kt square into 3 kb raised to 3 by 2 into t raised to 1 by 2 divided by 2 kt raised to 3 by 2. This is equal to 3 by 2 n kBt. Next question is, if the partition function of a harmonic oscillator with frequency omega at a temperature T is kt by h cut omega, then the free energy of n such independent oscillator is dash. So here it is given that the partition function Z1 is equal to kt by h cut omega. So the partition function of n such independent oscillator is Zn. This is equal to Z1 the whole raised to n. So this is equal to kt by h cut omega the whole raised to n. So here the free energy F is equal to minus kt ln Zn. This is equal to minus n kt ln of kt by h cut omega. So this is equal to n kt ln of h cut omega by kt. So the answer is option C. The next question is, the partition function of two Bose particles, each of which can occupy any of the two energy levels 0 and E is dash. Here there are three ways of arranging these two Bose particles. One way is that one Bose particle will stay in the 0 energy level and the other stay in the E energy level. The next possibility is that both the Bose particle will stay in the E energy level. Another possibility is that both the Bose particle will stay in the 0 energy level. So these are the three possibilities. So for the first possibility, the partition function can be written as e raised to minus e by kt. For the second possibility, that means when both the Bose particles will stay in the 0 energy level, then the partition function is e raised to minus 2 into 0 by kt. Then for the third possibility, the partition function is e raised to minus 2 e by kt. So the partition function is equal to e raised to minus e by kt plus e raised to minus 2 into 0 by kt plus e raised to minus 2 e by kt. So this is equal to 1 plus e raised to minus e by kt plus e raised to minus 2 e by kt. The next question is, the mean internal of a one-dimensional classical harmonic oscillator in equilibrium with a heat bath of temperature T is dash. So for a one-dimensional harmonic oscillator, the Hamiltonian H is equal to px square by 2m plus half kx square. So here we know that we have the two quadratic terms. Then by the equipartition theorem, each quadratic terms contribute half kBt. So here the mean internal energy is equal to 2 into half kBt. So this is equal to kBt. Next question is, a system of n localized non-interacting spin half ions of magnetic moment mu, each is kept in an external magnetic field H. If the system is in equilibrium at temperature T, then Helmholtz free energy of the system is dash. So here the energy of the ion is E is equal to minus mu dot H, and this is equal to mu H for spin minus half ion, and this is equal to minus mu H for spin half ion. So the partition function of an ion is Z1 is equal to e raised to minus mu h by kBt plus e raised to mu h by kBt. So this is equal to 2 cos h of mu h by kBt. So the partition function for n such non-interacting ions is Zn. This is equal to Z1 the whole raised to n. This is equal to 2 cos h of mu h by kBt the whole raised to n. So the Helmholtz free energy is F is equal to minus kBt ln of Zn. So this is equal to minus n kBt ln of 2 cos h of mu h by kBt. So the answer is option B. The next question is, the partition function for a gas of photon is given by ln Z. This is equal to pi square V kT the whole raised to 3 divided by 45 h cut cube c cube. Then the specific heat of the photon gas varies with temperature as, and the pressure of photon gas is dash. So here the partition function of the photon gas is ln Z is equal to pi square V kT the whole raised to 3 divided by 45 h cut cube c cube. So the internal energy is U is equal to kB T square into dou by dou T of ln Z, and this is equal to kB T square into dou by dou T of pi square V kT the whole raised to 3 divided by 45 h cut cube c cube. So this is equal to kB T square pi square V divided by 45 h cut cube c cube kB raised to 3 into 3 T square. And this is equal to 3 pi square V divided by 45 h cut cube c cube kB raised to 4 T raised to 4. And we know Cv is equal to dou U by dou T, and this is equal to 3 pi square V divided by 45 h cut cube c cube kB raised to 4 into 4 T cube. That is Cv is proportional to T raised to 3. So the answer is option B. And here the free energy F is equal to kBt ln Z, that is equal to kBt pi square by 45 V kT the whole raised to 3 divided by h cut cube c cube. The pressure P is equal to minus of dou F by dou V, and this is equal to kBt into pi square by 45 into V kT the whole raised to 3 divided by h cut cube c cube, and this is equal to pi square by 45 V into kT the whole raised to 4 divided by h cut cube c cube. So the answer is option C. The next question is, a system of n non-interacting classical point particles is constrained to move on the two-dimensional surface of a sphere. The internal energy of the system is dash. Since it is a two-dimensional system, then the number of degrees of freedom for n particles is equal to 2n. So the energy per degrees of freedom is equal to half kBt. This is by the equipartition theorem. So the internal energy of the system is equal to half kBt into 2n. So this is equal to n kBt. So the answer is option C. The next question is, consider a one-dimensional gas of n non-interacting particles of mass m with the Hamiltonian for a single particle is h is equal to p square by 2m plus half m omega square into x square plus 2x. The high temperature specific heat in units of R is equal to n kb is dash. So here h is equal to p square by 2m plus half m omega square into x square plus 2x, and this is equal to p square by 2m plus half m omega square into x plus 1 the whole square minus m omega square by 2. So here for a one-dimensional harmonic oscillator there is 2 degrees of freedom and there is n non-interacting gas. So the total degrees of freedom is 2n. Then by the law of equipartition of energy, E is equal to 2n into half kBt, and this is equal to n kBt, and this is equal to RT. So C is equal to dE by dt, and this is equal to R. So the answer is option A. The next question is, a two-level system has energy 0 and E. The level with 0 energy is non-degenerate while the level with energy E is triply degenerate. The mean energy of a classical particle in the system at a temperature T is dash. So here there are two energy levels 0 and E. Gi is the degeneracy. So the mean energy E is equal to summation over I Ei Gi e raised to minus Ei by kBt divided by summation over I Gi e raised to minus Ei by kBt. So here E is equal to 0 into 1 into e raised to minus 0 by kBt plus 3e into e raised to minus e by kBt divided by 1 into e raised to minus 0 by kBt plus 3 into e raised to minus e by kBt. So this is equal to 3e e raised to minus e by kBt divided by 1 plus 3 e raised to minus e by kBt. So the answer is option D. Next question is, consider a system whose three energy levels are given by 0, E and 2E. The energy level E is twofold degenerate and the two are non-degenerate. The partition function of the system with beta is equal to 1 by kBt is given by dash. Here the three energy levels are 0, E and 2E. The energy state E has the degeneracy 2. So, Z is equal to summation over I g of Ei e raised to minus beta Ei, and this is equal to 1 into e raised to minus beta into 0 plus 2 into e raised to minus beta e plus 1 into e raised to minus beta into 2e. So, this is equal to 1 plus 2 e raised to minus beta e plus e raised to minus 2 beta e, and this is equal to 1 plus e raised to minus beta e the whole square. So, the answer is option C. The next question is, a system has two energy levels with energies E and 2E. The lower level is fourfold degenerate while the upper level is doubly degenerate. If there are n non-interacting classical particles in the system which is in thermodynamic equilibrium at a temperature T, the fraction of particles in the upper level is dash. So here the partition function is equal to summation over I g of Ei e raised to minus Ei by kBt. And this is equal to 4 e raised to minus e by kBt plus 2 e raised to minus 2e by kBt. The fraction of particles in the upper level is equal to 2 e raised to minus 2e by kBt divided by 4 e raised to minus e by kBt plus 2 e raised to minus 2e by kBt. And this is equal to 1 plus 2 e raised to e by kBt plus 1. So the answer is option B. Next question is, consider a system of n non-interacting atoms each having an orbital angular momentum j is equal to 2. A constant magnetic field H is applied along the z-axis. The total number of microstate of the system is dash. So here it is given that j is equal to 2. Therefore omega is equal to 2j plus 1, and this is equal to 2 into 2 plus 1, this is equal to 5. For n such atom, omega n is equal to 5 raised to n. So the answer is option A. The next question is, the number of distinct arrangement of 6 boson placed in 3 energy state are. So for BE statistics, WBE is equal to GI plus NI minus 1 the whole factorial divided by GI factorial into NI factorial minus 1 the whole factorial. So this is equal to, so here NI is equal to 6 and GI is equal to 3. So this is equal to 3 plus 6 minus 1 the whole factorial divided by 3 factorial into 6 minus 1 the whole factorial, and this is equal to 8 factorial divided by 3 factorial into 5 factorial, and this is equal to 56. So the answer is option C. Next question is, in canonical ensemble, the system. In the microcanonical ensemble, there is no exchange of energy and the number of particles. That means it is a closed system. Then for a canonical system, there is only exchange of E. That means only exchange of energy. So this is the open system. Then for the grand canonical system, both energy and the number of particles exchange. So the answer is option B. Next question is, for motion of two particles moving in two-dimensional space, the phase space required to represent the state of particles must have at least. So here it is given that this is 2 particle and 2D space. So here F is the dimension and N is the number of particles. So the dimension of the phase space is equal to 2Fn, and this is equal to 2 into 2 into 2. So this is equal to 8 dimension. So the answer is option A. Next question is, which of the following relations between the particle number, density and temperature T must hold good for a gas consisting of non-interacting particles to be described by quantum statistics? So here the number density n is equal to n by v, and this is equal to n divided by 4 by 3 pi r cube, where n is the total number of particles. So r is approximately equal to n raised to minus 1 by 3. Here r is the interparticle distance. Then by the de Broglie wavelength, lambda is equal to h by p, and this is equal to h by square root over 2me, and this is equal to h by square root over 2m kBt, because here E is equal to kBt. For quantum states, R is approximately equal to lambda, that is n raised to minus 1 by 3 is approximately equal to lambda, that is lambda by n raised to minus 1 by 3 is approximately equal to 1. Substituting the value of lambda here, we can write h n raised to 1 by 3 divided by 2m kt the whole raised to 1 by 2 is approximately equal to 1. That is, n raised to 1 by 3 divided by t raised to 1 by 2 is approximately equal to 2mk the whole raised to 1 by 2 divided by h. This implies n divided by t raised to 3 by 2 is approximately equal to 2mk the whole raised to 3 by 2 by h cube. So this is approximately equal to 10 power 22. This implies n divided by t raised to 3 by 2 is greater than 1. So the option C is the correct answer. Next question is, a metal has free electron density n is equal to 10 power 29 meter raised to minus 3. Which of the following wavelength will excite plasma oscillation? Here, the plasma frequency omega p is equal to square root over n e square divided by epsilon 0 me. Me is equal to 9.109 into 10 power minus 31 kilogram. Epsilon 0 is equal to 8.854 into 10 power minus 12. E is equal to 1.602 into 10 power minus 19. N is equal to 10 power 29 meter raised to minus 3. Therefore, omega p is equal to square root over 10 power 29 into 1.602 into 10 power minus 19 square divided by 8 into 854 into 10 power minus 12 into 9.109 into 10 power minus 31. This is approximately equal to square root over 2.566 into 10 power minus 9 divided by 8.062 into 10 power minus 41, and this is equal to square root over 3.183 into 10 power 31, and this is approximately equal to 5.64 into 10 power 15 rad per second. That is, the wavelength lambda p is equal to 2 pi c by omega p. So lambda p is equal to 2 pi into 3 into 10 power 8 divided by 5.64 into 10 power 15, and this is approximately equal to 1.885 into 10 power 9 divided by 5.64 into 10 power 15. This is approximately equal to 3.34 into 10 power minus 7 meter. So here, converting the wavelength into micrometers, we can write lambda p is equal to 3.34 into 10 power minus 7 into 10 power 6 micrometer divided by 1 meter, and this is approximately equal to 0.334 micrometer. This value is closest to the option B, 0.330 micrometer. Next question is, consider the Fermi-Dirac distribution function at the room temperature where E refers to the energy. If EF is the Fermi energy, which of the following is true? F of E is equal to 1 by e raised to E minus EF by KT plus 1. Here T is equal to 300 Kelvin and E is equal to EF. Therefore, F of EF is equal to 1 by e raised to EF minus EF by KT plus 1, and this is equal to 1 by 2. So the answer is option B. Next question is, the wave function of two identical particles in state n and s are given by phi n of r1 and phi s of r2 respectively. The particles obey Maxwell-Boltzmann statistics. The state of the combined two-particle system is expressed as. In Maxwell-Boltzmann statistics, the particles are distinguishable. Hence, their wave functions do not overlap. So, the state of the combined two-particle system will be psi is equal to phi n of r1 into phi s of r2. So the answer is option D. Next question is, which one of the following is a fermion? For fermions, the sum of the number of protons, neutrons and electrons is odd, and for boson, the sum of the number of protons, neutrons and electrons is odd. Then for alpha particles, that is 2He4, the number of protons plus number of neutrons is equal to 2 plus 2, this is equal to 4, and this is an even number, that means this is a boson. Then for 4Be7, Np plus Nn is equal to 4 plus 3 is equal to 7, that is odd, so it is fermion. Then for H atom, that is 1H1, the number of protons plus number of electrons equal to 1 plus 1, and this is equal to 2, so this is a boson. Then for deuteron, that means it is a nucleus of deuterium, so this is 1H2. So this is equal to number of protons plus number of neutrons, here it is 1 plus 1 and this is equal to 2. So this is also a boson. So here the fermion is 4Be7. The next question is, the number of distinct ways in which 4 indistinguishable bosons can be distributed in 7 energy levels. For bosons, Omega is equal to n plus g minus 1 the whole factorial divided by n factorial into g minus 1 the whole factorial. So here n is equal to 4 and g is equal to 7. Therefore omega is equal to 4 plus 7 minus 1 the whole factorial divided by 4 factorial into 7 minus 1 the whole factorial. And this is equal to 10 factorial divided by 4 factorial into 6 factorial, and this is equal to 210. So the answer is option B. The next question is, a system of three indistinguishable particles has a total energy of 4E. There are four single particles energy states with energy 0, E, 2E and 3E. The number of microstates accessible to the system will be, let A, B, C be the three particles and the energy levels are 0, E, 2E and 3E. The first way of arrangement is C is staying in the 0 energy level and AB is staying in the 2E energy level. Then the total energy is 4E. The second possibility is AB is in the E energy level and C is in the 2E energy level. Then the total energy is 4E. Then the third possibility is B is in the 0 energy level, C is in the E energy level, A is in the 3E energy level. Then the total energy is 4E. So here there are three possible ways to get the energy as 4E. So the answer is option D. The next question is, the Fermi energy of a free electron as depends on the electron density rho as. Here the density of state is g of p dp is equal to 4 pi v by h cube p square dp, where p is equal to square root over 2me. Therefore g of e dE is equal to 4 pi v by h cube into 2me into m by 2e the whole raised to 1 by 2 into dE. Therefore g of e is equal to 4 into root 2 pi v by h cube into m raised to 3 by 2 e raised to 1 by 2. Electron has a spin degeneracy 2, so we need to multiply it by 2. So g of e is equal to 8 root 2 pi v by h cube m raised to 3 by 2 e raised to 1 by 2. And we know that the Fermi-Dirac distribution is f of e is equal to 1 by e raised to e minus ef by kt plus 1. At 0 Kelvin, f of e is equal to 1 when e less than ef and it is 0 when e greater than ef. Then the total number of particles is n is equal to integral over 0 to ef 8 root 2 pi v by h cube m raised to 3 by 2 e raised to 1 by 2 dE. Rearranging, we get n by v is equal to 8 root 2 pi by h cube m raised to 3 by 2 ef raised to 3 by 2 divided by 3 by 2. We know that n by v is equal to rho. So that rho is equal to 8 root 2 pi by h cube m raised to 3 by 2 ef raised to 3 by 2 by 3 by 2. That is, ef is proportional to rho raised to 2 by 3. So the answer is option B. The next question is, the probability that a state which is 0.2 eV above the Fermi energy in a metal atom at 700 Kelvin is dash. So the probability in the Fermi-Dirac statistics is P of E is equal to 1 by e raised to e minus ef by kBt plus 1. Here E minus Ef is equal to 0.2 electron volt and E is equal to 700 Kelvin. Therefore P of E is equal to 1 divided by e raised to 0.2 into 1.6 into 10 power minus 19 divided by 1.38 into 10 power minus 23 into 700 plus 1. So this is equal to 1 by exponential of 2 into 1600 divided by 138 into 7 plus 1, and this is equal to 0.035. So the answer is option C. The next question is, the pressure for an non-interacting Fermi gas with internal energy U at temperature T is dash. If U is the total internal energy density, then pressure is equal to 2 by 3 U, that is equal to 2 by 3 U by V, where U is equal to small uv. So the answer is option B. Next question is, a system of non-interacting Fermi particles with Fermi energy EF has the density of states proportional to root E, where E is the energy of a particle. The average energy per particle at the temperature T is equal to 0 is dash. So here it is given that G of E is proportional to root E. That is, G of E is equal to A root E, where A is a constant. So the average energy per particle at T is equal to 0 Kelvin is E is equal to integral over 0 to EF E into F of E into G of E into dE divided by integral over 0 to EF F of E into G of E dE. At t is equal to 0, f of e is equal to 1 when e less than ef, and it is equal to 0 when e greater than ef. So e is equal to a integral over 0 to ef e root e dE divided by a integral over 0 to ef root e dE. Cancelling a on the numerator and denominator, we can write this is equal to integral over 0 to ef e raised to 3 by 2 dE divided by integral over 0 to ef e raised to 1 by 2 dE, and this is equal to 3 by 5 ef. So the answer is option D. Next question is, for a two-dimensional free electron gas, the electronic density N and the Fermi energy EF are related by. So here the density of state in 2D is G of P dP is equal to 2 pi A by H square P dP, and P is equal to square root over 2me and dP is equal to square root over m by 2e dE. Therefore G of E dE is equal to 2 pi A by H square root over 2me square root over m by 2e dE, and this is equal to 2 pi A by H square m dE. And we know that the spin degeneracy is equal to 2. So that multiplying with 2, we get G of E is equal to 4 pi A by H square m. That is, the number of particles N is equal to integral over 0 to infinity f of E G of E into dE. And here f of E is equal to 1 when E less than EF, and it is 0 when E greater than EF. Therefore N is equal to 4 pi A by H square into MEF. Therefore N by A is equal to 4 pi EF m by H square, and this is equal to N, because here N is equal to capital N by A, that is the electronic density in 2D. So N is equal to 4 pi m EF by H square, and this is equal to 4 pi EF by H cut into 2 pi the whole square. Therefore N is equal to m EF by pi H square. Therefore the answer is option B. Next question is, consider degenerate Fermi gas at T is equal to 0 with the Fermi energy EF. The mean energy per particle will be dash. We know that the mean energy E bar is equal to D divided by D plus S into EF, and for 3D, D is equal to 3, and for non-relativistic, S is equal to 2. Therefore E is equal to 3 divided by 3 plus 2 into EF. Therefore E bar is equal to 3 by 5 EF. So the answer is option A. The next question is, consider ideal Fermi gas in 3 dimension. The density of energy state and is proportional to dash. Here dimension D is equal to 3, and for Fermi gas S is equal to 2. So the density is proportional to E raised to D by S minus 1. That is, D is proportional to E raised to 3 by 2 minus 1, that is D proportional to E raised to 1 by 2. So that the answer is option A. Next question is, total energy E of an ideal non-relativistic Fermi gas in 3 dimension is given by E proportional to n raised to 5 by 3 divided by V raised to 2 by 3, where n is the number of particles, V is the volume of gas. Identify the correct equation of state, P being the pressure. So here it is given that E is proportional to n raised to 5 by 3 divided by V raised to 2 by 3. Therefore E is equal to K into n raised to 5 by 3 divided by V raised to 2 by 3. And we know that P is equal to minus dou E by dou Y. That is equal to 2 by 3 K into n by V the whole raised to 5 by 3. That is, P is equal to 2 by 3 into K by V into n raised to 5 by 3 divided by V raised to 2 by 3, and this is equal to 2 by 3 into E by V. That is, PV is equal to 2 by 3 E. So the answer is option B. The next question is, for a Fermi-Dirac distribution, the probability of occupation of a single particle energy level is equal to dash. So for the Fermi-Dirac distribution, the probability of occupation of a single particle energy level is equal to the half average occupancy of that level. So the answer is option C. The next question is, if the temperature of a free electron gas is increased by a factor of 2, its specific heat increases by a factor of dash. We know that Cv is proportional to T raised to 3. So when temperature is doubled, that means temperature is increased by a factor of 2, that means T is increased to 2T, then Cv is proportional to 8T raised to 3. That means the specific heat increases by a factor of 8. So the answer is option C. The next question is, a Fermi wave vector kf of an ideal gas of n molecules enclosed in a volume V at temperature is equal to 0 Kelvin obeys the relation. In 3D, kf is equal to 3 pi square n by v the whole raised to 1 by 3, and this is equal to constant into n by v the whole raised to 1 by 3. So the answer is option A. The next question is, the temperature of a cavity of a fixed volume is doubled. Which of the following is true for the black body radiation inside the cavity? Number of photons n1 is proportional to t cube and energy of photons E1 is proportional to t raised to 4. When the temperature is doubled, n2 is proportional to 2t the whole cube, that is equal to 8t cube, and this is equal to 8 into n1. And the temperature E2 is proportional to 2t the whole raised to 4, and this is equal to 16t raised to 4, and this is equal to 16E1. So the answer is option C. The next question is, the spectrum of radiation emitted by a black body at a temperature 1000 Kelvin peaks in the. By Wien's displacement law, lambda max is equal to 2.897 into 10 power minus 3 divided by t, and this is equal to 2.897 into 10 power 3 divided by 1000, and this is equal to 2.897 into 10 power minus 6 meter, and this is equal to 2897 Armstrong. That is, the wavelength lies in the infrared region. So the answer is option B. The next question is, for a black body radiation in a cavity, photons are created and annihilated freely as a result of emission and absorption by the walls of cavity. This is because photons have zero chemical potential, so the number of photons cannot be conserved. Thus, the photons can be created and annihilated. So the answer is option A. The next question is, if Planck's constant were 0, then the total energy contained in a box filled with the radiation of all frequency at temperature T would be. So here, energy in the case of the black body radiation is E is equal to h omega divided by e raised to h omega by kt minus 1. When h tends to 0, then E is in the 0 by 0 form. So we need to apply the L'Hospital rule. That is, E is equal to limit h tends to 0 h omega divided by e raised to h omega by kt minus 1, and this is equal to limit h tends to 0 h omega divided by e raised to h omega by kt into omega by kbt. So this is equal to kt divided by 1, and this is equal to kt. So the answer is option D. Next question is, consider a system of 4 spins with spin s is equal to half and magnetic moment mu each. It is placed in an external magnetic field H. The magnetic moments can either be parallel or anti-parallel to the magnetic field. Consider a macro state of the system with energy 2 mu h. Using the postulate of equal a priori probability, the probability of finding the system with magnetic moment minus 2 mu is given by dash. So here the system has n is equal to 4 spins with each magnetic moment mu that can be parallel or anti-parallel to the external magnetic field H. So the total magnetic moment M depends upon the number of spins that is pointing upwards and downwards. So here it is asking about the probability of the system having a total magnetic moment of minus 2 mu. The total magnetic moment M is equal to n spin up of mu plus n spin down of minus mu. Capital N is equal to n spin up plus n spin down, that is equal to 4. Therefore, n spin down is equal to 4 minus n spin up. That is, M is equal to n spin up into mu minus 4 minus n spin up into mu, and this is equal to 2 n spin up into mu minus 4 into mu. Here we need to find the number of states with m is equal to minus 2 mu. That is, substituting the value of m is equal to minus 2 mu here, we can write minus 2 mu is equal to n equal to 2 into n spin up into mu minus 4 mu. That is, 2 mu is equal to 2 n spin up into mu. That is, n spin up is equal to 1. So To get the total magnetic moment minus 2 mu, we need to arrange the three spins pointing anti-parallel and one spin should point parallel to the field. Then the number of ways to arrange the n upspins and n downspin is given by the binomial formula, that is W is equal to n spin up, and this is equal to n factorial divided by n spin up factorial into n minus n spin up the whole factorial. For n is equal to 4 and n spin up is equal to 1, we can write this is equal to 4 factorial divided by 1 factorial into 4 minus 1 the whole factorial. This is equal to 4 factorial divided by 1 factorial into 3 factorial is equal to 4. That is, here there are 4 microstate for the macro state having a total magnetic moment of minus 2 mu. The total number of possible microstates for the entire system is 2 raised to n. Here n is equal to 4, so W is equal to 2 raised to 14 is equal to 16. So the probability is equal to W of 1 divided by W total, and this is equal to 4 divided by 16. This is equal to 1 by 4. Next question is, consider a paramagnetic salt with n magnetic ions each with the spin half at t is equal to 0 in the presence of an external magnetic field H. At t is equal to 0, all spin will align along the direction of the applied magnetic field. So the answer is option A. Next question is, consider a crystal of n atoms with spin quantum number delta is equal to half and m delta is equal to plus or minus half. The magnetic moment of the ith atom is where G is the Landé G factor and mu b is the Bohr magneton. Assuming that the atoms do not interact appreciably but are in the thermal equilibrium at temperature T and are placed in an external magnetic field H is equal to H Z cap, then the partition function is dash. So here the energy of the magnetic moment mu in an external magnetic field H is given by E is equal to minus mu dot H, and it is given that H is equal to Hz cap, and we can write the Z component of the magnetic moment as mu Z is equal to plus or minus G mu B by 2. So the two energy levels for a single atom are, for E plus this is equal to minus mu Z into H, and this is equal to minus G mu B H by 2, and E minus is equal to minus of minus mu Z H is equal to G mu B H by 2. So the partition function of a single atom is Z1 is equal to summation over I e raised to minus beta ei, and this is equal to e raised to minus beta e plus plus e raised to minus beta e minus. And substituting the value of e plus and e minus, we can write it as Z1 is equal to e raised to beta into G mu b h by 2 plus e raised to minus beta G mu b h by 2. Then use the hyperbolic cosine formula, that is cos hx is equal to e raised to x plus e raised to minus x by 2. And here Z1 is equal to 2 cos h of beta G mu b h by 2, and this is equal to 2 cos h of G mu b h by 2 kt. Therefore, for n atoms, the total partition function Zn is equal to Z1 the whole raised to n, and this is equal to 2 cos h of G mu b h by 2 kt the whole raised to n. So the correct option is option B. Next question is, consider 5 independent magnetic moment. Each moment has only 2 direction, plus m and minus m. The Hamiltonian of such system is given by x is equal to summation over I equal to 1 to 5 mi. If the total magnetization of the system is equal to m, the entropy is equal to. So here in this case, each magnetic moment has 2 possible direction, that is plus m and minus m. So for 5 independent magnetic moments, there are 2 raised to 5, that is equal to 32 possible configuration. So the answer is option A. The next question is, which of the following conditions should be satisfied by the temperature T of the system of n non-interacting particles occupying a volume V for Bose-Einstein condensation to take place? For Bose-Einstein condensation, temperature Tb is equal to h square divided by 2 pi mk into n divided by 2.612 v the whole raised to 2 by 3, and this is equal to h square divided by 2 pi mk n by v Raymond's zeta function of 3 by 2 the whole raised to 2 by 3. For Bose-Einstein condensation, temperature should be less than Tb. That is T less than Tb. That means T less than h square divided by 2 pi mk into n by v Raymond zeta function of 3 by 2 the whole raised to 2 by 3. The next question is, which of the following atoms cannot exhibit Bose-Einstein condensation even in principle? Here we need to check the value of the sum of Np, Ne and Nn. So here for 1H1, Np is equal to 1, Ne is equal to 1, Nn is equal to 0. So the sum of Np, Ne and Nn is equal to 2. So this is an even number. Then for 2He4, Np is equal to 2, Ne is equal to 2, Nn is equal to 2, and their sum is 6. It is also even. Then for sodium, Np is equal to 11, Ne is equal to 11, Nn is equal to 12. Then sum is equal to 34. It is also an even number. Then for 19K40, that is potassium, Np is equal to 19, Ne is equal to 19, Nn is equal to 21, then their sum is 59, it is an odd number. So as it is an odd number, it cannot exhibit Bose-Einstein condensation. So the answer is option D. Next question is, in Bose-Einstein condensate, the particle for bosons, the interparticle distance is comparable to the de Broglie wavelength. So their wave function overlap. So the answer is option C. The next question is, the large number n of the ideal bosons, each of mass m, are trapped into three-dimensional potential V of r is equal to m omega square r square by 2. The bosonic system is kept at temperature T, which is much lower than Bose-Einstein condensation temperature Tc. The chemical potential mu satisfies. For boson, the energy E nx ny nz is equal to nx plus ny plus nz plus 3 by 2 into h cut omega, where nx, ny, nz is equal to 0, 1, 2, etc. The ground state energy of each boson is E is equal to 3 by 2 h cut omega. For Bose-Einstein condensation to occur, the chemical potential should be equal or less than the ground state energy. That means mu is less than or equal to 3 by 2 h cut omega. So the answer is option A. The next question is, the critical temperature for the Bose-Einstein condensation depends on the density of particles as. Here we know that the critical temperature for the Bose-Einstein condensation is Tc is equal to 2 pi h cut square divided by mkb into n by Raymond zeta function of 3 by 2 the whole raised to 2 by 3. That means Tc is proportional to n raised to 2 by 3, where n is the number density. So we can say here the answer is n raised to 2 by 3. The next question is, if the temperature of a black body enclosure is doubled, the total number of photons in the enclosure increases by a factor of dash. In black body radiation, number of photons is proportional to T raised to 3. That is, n1 by n2 is equal to T raised to 3 divided by 2T the whole raised to 3. Because here it is mentioned that the temperature is doubled. So this is equal to T raised to 3 divided by 8 T raised to 3. That means n1 by n2 is equal to 1 by 8. That is, n2 is equal to 8 n1. So the answer is option D. The next question is, which of the following is an example of a first order phase transition? The liquid gas phase transition at the critical point is a first order phase transition. A paramagnetic to ferromagnetic phase transition is a second order phase transition. A normal metal to a superconductor phase transition is a second order phase transition. A liquid gas phase transition away from the critical point is a second order phase transition. So the answer is option A. The next question is, a second order phase transition is one in which The entropy and volume are the first derivatives of the Gibbs free energy, that is S is equal to minus dou G by dou T at constant pressure and V is equal to dou G by dou P at constant temperature. Then, for the second order phase transition, both are continuous. The specific heat at constant pressure Cp and the isothermal compressibility kappa T and the coefficient of the thermal expansion alpha P are the second derivatives, that is Cp is equal to T into dou S by dou T at constant pressure, kappa T is equal to minus 1 by V into dou V by dou P at a constant temperature, alpha P is equal to 1 by V into dou V by dou T at constant pressure. So, for a second order transition, these show a discontinuity or a sharp peak. So, the answer is option B. The next question is, a first order phase transition is characterized by dash. The first order phase transition is characterized by the divergence of the specific heat at Tc, the critical temperature. So, the answer is option A. In the first order phase transition, at the transition temperature, the specific heat of the system is dash. The specific heat diverges for both first order and second order phase transition. The entropy has a finite discontinuity for first order phase transition, whereas it is continuous for second order phase transition. So the answer is option B. Next question is, across a first order phase transition, the free energy is continuous, but the derivative is discontinuous in the first order phase transition. So the answer is option C. The next question is, the high temperature magnetic susceptibility of solids having ions with magnetic moments can be described by chi proportional to 1 by T plus theta, with T as absolute temperature and theta as constant. The three behaviors, that is the paramagnetic, ferromagnetic and antiferromagnetic, are described respectively by. For a paramagnetic material, the susceptibility chi is proportional to 1 by T and here theta is equal to 0. And for a ferromagnetic, chi ferro is proportional to 1 by T plus theta, where theta less than 0. And for antiferromagnetic material, theta is greater than 0. So the answer is option C. This is the end of this video. Thanks for watching this channel.